Good morning, Pirates. Today we're going to talk about ionic compounds and how to write their formulas and to name them. If you remember, an ionic compound forms between a cation and an anion, and it contains what's called ionic bonds. Okay? These are formed basically when electrons are transferred. So when the cation gives away the electrons and the anion takes it, ions are formed, and that's the beginning part of an ionic bond. So let's just review our two types of ions, and I'll show you an example in just a moment. A cation is a positive ion, and you can remember that because cats have paws. An anion is a negative ion. So you will start to see after our example today that metals tend to form cations and nonmetals form anions. So I think this example will help. If we look at lithium and fluorine's Bohr model, okay? If we go to our periodic table, lithium is over here, element number 3. Since it's atomic number 3, we know it has 3 protons and 3 electrons. So if we look at its structure, we see 3 protons in the middle, and those 3 electrons around the outside. We see 2 in the first energy shell and 1 in this outer energy shell. Okay? But don't forget the lovely octet rule that says atoms want 8 outer or 8 valence electrons to become stable. So since lithium only has 1 electron in this outer shell, it's not very stable. Now, if we look at fluorine. Fluorine is atomic number 9, which is why you see the 9 protons here in the middle. And if you count up the total electrons, there's 2 on the inner energy shell, and there should be 7 around the outside. So we have lithium that has 1 valence electron, and we have fluorine that has 7 valence electrons. And you can see neither of which have reached their octet or have 8 valence electrons. However, you could start to see how this can form a partnership. If lithium were to give up this electron and give it to fluorine, now fluorine would have 8, and lithium would no longer have that electron. So if you look here in the next visual, you see now lithium has lost this outer energy level. It is no longer gone, and it has a duet because that first energy level, remember, can only hold a maximum of 2. And now if we count fluorines, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, or fluorine now has its full octet and it's stable. So now let's look at the charges since this occurred. Okay, lithium has 3 protons, so a positive 3 charge because protons are positive, and now it only has 2 electrons. It used to have 3, but it gave up this extra one here to fluorine. So it only has 2 electrons, which are negatively charged. And in math, if we take positive 3 minus 2, we get a positive 1 overall charge. Now fluorine still has the 9 protons, so positive 9. However, instead of having 9 electrons like the neutral fluorine atom did, it now has an extra electron, so it has 10 electrons total if you count it up, and that's 10 negative particles. So if we take negative 10 plus 9, we get a negative 1 charge. So these are now ions. It's an atom with a charge. Lithium has a plus 1 charge, and fluorine has a negative 1 charge. So you can see that written right here, Li plus 1 and fluorine negative 1. Okay, now since we know opposites attract, they're going to make a perfect ionic compound. Now, the rules with an ionic compound is the charges have to balance out or equal 0. All compounds have to be neutral. So if we have lithium plus 1 because it lost an electron, and fluorine negative 1 because it's gaining an electron, positive 1 and negative 1 add up to 0, So we only need one atom of each of these, or one lithium ion and one fluorine ion. So the formula is LiF. We don't write ones, they're assumed. Okay, now the nice thing is above your periodic table, you have these charges already written for you. Okay, we just looked at lithium. Lithium up here is a +1 charge, or it forms a +1 ion. Well, you can imagine all these alkali metals react in the same way, because if we were to draw their Bohr model, since they're in column 1, or family 1, they have 1 valence electron. Since they want 8, it's going to be easier if they give up that 1. So all of the alkali metals will form a +1 charge when they're trying to form a compound. If you look above column 2, they're going to lose 2 electrons or form a +2 to become stable. So it's opposite of money, right? Because they're losing negative particles, losing negative electrons. That's why they're becoming positive. Whereas if you lose money, you become bankrupt, right? Or you go in debt. So I always think it's opposite of money. Okay, the other example we were looking at with lithium here was fluorine. So if we go over to the halogens, group 7 over here on the periodic table, you'll see above fluorine, there is this -1 charge, and that would account for all of the halogens. Chlorine has 7 valence electrons since it's in the 7th family, so it needs 1 more to become stable and will also form a -1 ion. So you can find the charges above the columns on the periodic table. These transition metals, you can see, do not have a charge above them, and we will be talking about that at a future date. So let's go over the basic rules now for ionic formulas. I wrote these 3 steps down to help you. First, you want to write the cation, the positive ion, or the ion from the left side of the periodic table comes first, because you read left to right. Then you want to write down the negative anion from the nonmetal. And this is only for simple ionic formulas. And you want to make sure you balance the charges to 0. So let's look at our example here. I gave you potassium chloride. And we'll talk in a moment why it doesn't say chlorine. But for now, you can know it's the same element. So first step is to write the positive charge. So we go over here to K. Potassium is K, the symbol, and the charge above it is +1. So right below here, under potassium, I'm going to write K +1. Second step, write the anion. We're going to look for chlorine over here to the right. And chlorine is Cl, and its charge for an ion is going to be -1. It wants to gain an electron to become stable. So chlorine, -1. So now we're going to balance those charges, okay? +1 and -1. We know balances out to 0 already. 1 plus -1 is 0. So we only need 1 potassium and 1 chlorine atom. However, we don't write the ones. So our final answer is KCl. Now, let's look at a more complicated one. Let's look at magnesium oxide. If we find magnesium on the periodic table, it's element number 12, and we see above there it has a +2 charge. So right below magnesium, I'm going to write Mg +2. Second step is to write the anion or the nonmetal with its negative charge. So oxide is oxygen. So I find oxygen over here, it's element number 8, and it has a -2 charge. So oxygen, -2. +2 and -2 we know also equals 0, so we only need 1 magnesium atom and 1 oxygen atom. So the final answer is MgO. Notice each individual element is capitalized. So capital M to show for magnesium, the G is lowercase because it has a second letter, and capital O to show that we're talking about oxygen. Now we have an easier way, something called the crisscross method. Okay, I'm going to open up a new document here to show you the shortcut here of the crisscross method. Okay, if we have aluminum and sulfur in a compound. First step is to look up the charges. So we find aluminum, element number 13 over here, trace to the top, and it says +3. So I'm going to go over here and write aluminum +3. Then I'm going to find sulfur, element number 16, trace up to the top, and we see it says -2. Sulfur, -2. It wants to gain 2 in order to reach its octet. Now, we have to think of a common multiple here that will eventually add to 0, because +3 minus 2 gives us a +1. So I know 3 and 2 both multiply into 6. So if I have 2 of these aluminums, they would add up to a +6. And if I have 3 sulfurs, 2, 4, 6 adds up to -6. +6 and -6 equals 0. So now when we're looking at writing the formula, you see here that I have 2 aluminum atoms, so it's Al2, or ions, sorry. And we have 3 sulfur ions, so S3. And this would be the final answer. Okay, but I mentioned there's this crisscross method, okay? The crisscross method is a shortcut, but there is something you have to be aware of. With the crisscross method, the first 2 steps are still the same. You're going to write your 2 charges. Your cation, aluminum +3. Your anion, sulfur -2. The third step is not the same. You're not going to balance the charges to 0. Instead, you're just going to take the absolute value of the superscript or charge and crisscross them. What I mean is if we take this 2, it's going to cross down and become the new subscript for aluminum. And this 3 is now going to become the new subscript for sulfur. So our final answer would be Al2, S3. Should look familiar because it's what we received doing it our normal way, which is balancing the charges. The only thing you have to be careful with the crisscross is you always want to check if you have to simplify the subscripts. So 2 and 3 cannot be reduced to anything else. However, because they both can't be divided by the same number, let's look at magnesium and oxygen. We looked at this earlier. Magnesium here is a +2. Oxygen is a -2. +2 and -2. If you were to do the crisscross method and just take the absolute value and cross the 2 down here and the 2 down here, you would get Mg2O2. However, we know that you can divide both of those subscripts by 2 and simplify them to Mg1O1, which we write like this. So you have to check with the crisscross method whether or not you can simplify. So if you remember here, we looked at magnesium oxygen and we received the same answer right now, MgO, whether you're doing it the neutral way or the crisscross way. So I'm going to add up here. Step 3 is either balance charges or crisscross and simplify. One last thing I do want to point out, these subscripts are how many atoms are in this final compound. So in this compound here, there is 1 magnesium atom and 1 oxygen atom. In this compound before, 2 aluminums and 3 sulfurs. That is how you write an ionic formula. Let's now look at the naming. Okay, naming is pretty simple. You're going to first name the cation as it is on the periodic table, and then you're going to write the name of the anion as it is on the periodic table, except to show that it's now part of a compound, you are going to change its ending to IDE. So for example, if I give you this formula, NaCl, you know how many elements there are by looking at the capital letters. So this is a new element, this is a new element. Okay, so we find Na on the periodic table. You'll start to notice we use a lot of the same ones over and over. So if we find sodium over here, Na is called sodium. So it says go ahead and write the name of the cation. So Na is called sodium. Second step, write the name of the anion. So Cl, in case you forgot, is way over here, and it's chlorine. Okay, except to show that it's now bonded and it's made a new complete substance, a new compound, we're going to change the ending to IDE. So instead of it being chlorine, that N changes to a D, chloride, as you see down here by the salt shaker. All those anions, for the most part, change to IDE. The halogens are the easiest. Bromine, bromide. Sulfur, sulfide. Chlorine, chloride. Some of them get a little tricky, though, like oxygen. Instead of oxygen, it becomes oxide. Okay? So here's the list of the common anions. Sulfur, sulfide. So you just change the ending or the suffix. And then, like I said, the halogens are the easiest. Chlorine, chloride. Bromine, bromide. So another one I would recommend here is nitrogen. Becomes nitride. It doesn't become nitrogide. And you'll start to get used to these as you see them. So let's try a couple here. CaCl2. The first element, Ca is called calcium. Second one's chlorine. However, since it's part of an ionic compound, we're going to change the ending to IDE. SRO. Sr is strontium. Keep the name as it is on the periodic table. The cations always stay the same. And instead of oxygen, it becomes oxide. Last one, NaI. Na is sodium, and the I becomes iodide. So instead of INE, it becomes IDE. Hope that helps. Have a wonderful day. Go Pirates.